Good afternoon. Welcome back, everyone. We hope that you all had a very enjoyable lunch and are ready for the afternoon sessions. The Germans just Frankensteined DeepSeek's R1 and V3 models into something called R1T Chimera. That was one of the responses on X after TNG released its first own large language model. What is referred to as Frankensteining by this post is something that we call the assembly of expert method. And it was developed at TNG, and it enabled the release of our first two own large language models in an open whale model. But as Hendrik put it in his earlier talk today, it was a great idea and not enough time. And even though Robert and Hendrik both were closely following each step of the project, day and night, even they probably wouldn't have been able to pull off such a success story without the support of a strong team behind them. Because somebody still needs to figure out all the nitty-gritty details between their initial idea and the release of a truly open-weight, state-of-the-art large language model. Besides management support, a project like this requires competent engineers that can put the ideas into practice and overcome all the conceptual and technical challenges that arise on the way. And with that, I finally bridge the gap to our speakers today, because David Reiss and Fabian Klemm are part of the team at TNG that works full-time on the actual disassembly and reassembly of the DeepSeek models that resulted into the Chimera models. And they are here today to talk about their learnings from putting this into practice. In total, they have assembled over 80 different models over the last half year, and I'm sure there's plenty to learn for us from their experiences of enabling something like this in a reproducible way. So with that, please enjoy the talk and give a warm welcome to David and Fabian.
Yes, thanks also from our side. A very warm welcome. Thanks, Jonathan, for the nice introduction. So I'm Fabian. I'm one small part of our AI research team. I've been with TNG now for 5.5 years. And happy to be here today with my colleague David.
Yeah, hi.
Hand over.
Hi, I'm David. As you might already guessed from the introduction by Jonathan and Fabian. And before we dive into the details, let me give you first a brief overview over who we are, what we, the TNG AI research group, do in general, and what Fabian and me will talk about. So, at the core, our team consists of, as you've maybe heard this morning, TNG managing directors Henrik Klages and Robert Dahlke, then also Benjamin Merkel, who's also giving a talk right now, and Lars Reimann, who's maybe sitting in the audience.
Stand up.
Yeah, here. He's over there. Yeah, and on our journey, we also got help and contributions by Dan Zecher, Daniel Klingmann, and TNG associate partner Sven Rohr. So our team was only founded at the beginning of this year by Henrik and Robert, and since then we published already 2 research articles and 2 open weights large language models, or LLMs in short. And here's an outline of our journey and of this talk. So first, Fabian and me will tell you about the basics, so mixture of experts and the DeepSeek architecture. Then second, we'll tell you about our first accomplishment, mixture of tunable experts. Third, which is also quite important, also for us nerds, is tooling. So from hardware through software up to serving customized LLMs. Fourth, we will tell you how to merge 2 or more LLMs into a new model. Fifth, we'll tell you about the Chimera models in particular. And sixth, we'll tell you how to enable tool calling. So with this, let's dive into the details. You probably all have heard that virtually all modern LLMs are based on the transformer architecture, but training larger and larger models requires enormous amounts of resources. This is one of the reasons why so-called mixture of experts transformers gained popularity in recent times. And Daria Soboleva, who is maybe also in the audience, I'm not sure, She'll give a talk exactly about mixture of experts at 4:15. So if you're interested in more details, attend her talk. But for now, let's only have a quick look at the architecture to understand how mixture of experts, in some sense, solve this problem of scaling large language models. So the classic transformer architecture consists here of, in principle, or essentially, two different kinds of layers which then repeat. So self-attention layers and feed-forward neural networks. And for example, when a user asks a question to the chatbot, this input first gets pre-processed. Each of its parts, called tokens, get converted into a vector. And then after this pre-processing, this vector is fed into this first self-attention layer, which in some sense mathematically captures the context of this token, and then adds the result of this computation to the input. This is then normalized, and then this is fed to this FFN here. This FFN somehow enriches this vector with related information which got trained into this FFN during the training of the large language model. And then afterwards, there's again both results added and normalized, and then this process repeats. So the point is, in this classic architecture here, this is called a dense transformer, because no matter what the input, always the same computations performed. So again, self-attention, adding and normalizing, the feed-forward network, and so on. And during these computations, all of the millions or billions or even trillions of parameters of these large language models are always used to perform these computations. This somehow sounds inefficient, right? And maybe when you think back to when you learned programming, what was one of the first things you learned? That was if-else statements, conditional computations, right? And maybe you already have an idea what I'm hinting here at. This is exactly the idea of mixture of experts. So in this architecture, you also have self-attention layers and these add and normalize layers, but these large FFN blocks are split somehow or replaced by several smaller FFNs, which are also called experts. And then there's an additional component, the router, which, as the name suggests, decides where to route an input. And the key point is that the router not only activates all of these smaller parts, which are also called the experts, but only a subset of them, like an if-else statement. And depending on the input, other experts get activated. So, of course, this innovation comes with new challenges. Yeah? For example, during training, it's difficult to, for example, ensure both that these experts get specialized really and all of them get utilized. And to address these challenges, the Chinese AI company DeepSeek introduced some very important innovations in this field into their own models. So let's have a quick look at DeepSeek architecture. First, in comparison to earlier models, for example, by Mistral, the French AI company, they increased the number of experts, of routed experts, to 256, while they at the same time decreased the number of activated, or the ratio of activated experts in each layer for each token to 8. So they increased somehow the sparsity of activation. And they have a special kind of routing mechanism, actually. So for each expert, for each routed expert, they compute, depending, again, on the input, an activation score, which is depicted here and denoted as P. And for each token in each layer, these 8 experts get activated, which got the highest scores. And afterwards, after they produce the output, this activation score is multiplied with the output, or the output is multiplied with the activation score, and then all the results are added. Beside that, they, as Henrik and Robert mentioned this morning, they introduced so-called shared FFNs, or shared experts, which get always activated no matter what the input. So again, if one gets another input, then other of these experts get activated. And we not only got interested in DeepSeek models because the architecture has many components to play with, but an important point for us was also that DeepSeek published in a short time a series, a whole bunch of different models, which are all based on this same architecture. So the models differ by the values of their weights and biases, but they share the same architecture. So at first, at the end of last year, they published V3, which is a non-reasoning model, at that time state-of-the-art. And shortly afterwards, already in January, as Henrik and Robert mentioned, they published R1. This was a part of the huge hype around DeepSeek. And the point of this model was that it is a reasoning model in comparison to V3. Then shortly afterwards, in March, they published an update of V3, and this is now a long-time member still of the OpenRouter leaderboard. So very popular model. And for example, in our work, we use it still today. And in May, they published an update of R1, R1 0528, also at the time state-of-the-art. And in August, they published v3.1, which interestingly both supports a reasoning mode and a non-reasoning mode. And the success story of DeepSeek continues. And but these are the most important models for us. And how we use them, will tell you Fabian in a moment.
All right. Thanks. Yes, so January this year, feels like ages ago, this was the moment it started for us. And I would like to start with a quote by Jan Koum, who is a co-founder and creator of WhatsApp. I think that you all know. And I once attended a talk by Jan, and he said it started all with the iPhone, with him buying an iPhone. And that was around 2009. The iPhone was brand new, and he was actually unemployed and had no idea what to do with his life. And from, let's say, his last money, he bought this iPhone. And he had this in his hand, and he thought, wow, this is so much more powerful than anything I had before in this kind. And he immediately asked himself, what can I do with that? How can I utilize this for my purposes? And that is how the whole WhatsApp story started. And I think to some extent we had a similar feeling in January. When R1 came out, we understood that this changed the open weight market. Not only us, also the stock market understood this. And so we immediately thought, okay, what can we do with that? How can we utilize this for our purposes, for the purposes of our clients? And what we started is, okay, we want to have a closer look. Let's look at it. Let's look into it. And that's what we did. So we started to create this kind of brain scan images. So what you could see here is, let's call it a brain scan of a DeepSeek model when you prompt it with some prompt. We have here depicted the activations of the experts that David just explained. So meaning from top to bottom, we have the in total 58 layers for experts that we have. And from left to the right, we have in total 256 experts per layer. So each of the pixels here depict one expert in our model, which are in total roughly 15,000. And now, if one of these pixels shines brightly, this means that this expert is really active, that it was used heavily, whereas when it's dark blue, it was not used at all. And of course, by just looking briefly at this image, you immediately see this is not a homogeneous setting. There are experts that clearly shine out and others that are just silent, totally silent. So that was one interesting first fact that we observed. So next question. What can we do with it? How could we utilize this now? And well, there's one thing, of course, about the DeepSeek models, which is not unique to DeepSeek models. They are aligned in some sense, right? So alignment is a typical thing everyone does, meaning if you ask any LLM how to build a bomb, it should not tell you. And with DeepSeek, there comes in something, let's say, more special. If you ask certain historical questions about certain historical events, let's say in the Cold War, it also will sometimes not tell you the answer. It will just say, I'm sorry, I can't tell you. Whereas we observed that this is not that clear. There are really similar questions when you ask it and it tells you the facts. It seems to know the facts, just sometimes it refuses to tell them. And we thought, hey, that's weird behavior. How do those compare? Comparing in that sense. And that is what we did. So we looked at the difference of activations between two classes of prompts. Once we give it prompts where it refuses, it says, I'm sorry, I can't answer. Then we give it prompts where it does tell us the facts. And then we look at the difference of activations and look at those. So this means now, when here somebody shines out, I mean, this is Mr. Doom by Henrik, right? When somebody shines out here, this expert was really active in the prompts where it says, I'm sorry, but was almost inactive in the prompts where it gave us the facts. So we thought, hey, we might not like this guy. He's maybe the guy who prevents our LLM from giving us the answer that we are desiring. So what could we do? First, we identify just a few of them. So here we put like the 10 most distinctive experts. And then what we did is we just switched them off. Just switching them off. And this is how we got the results. So this is from our first article that we published this year in, I think, March. And the key result is that in this particular case, in 40% of the prompts, the refusal could be deactivated. So the LLM started to give us the answer in 40% of the cases by only, and this is the important fact, by only deactivating 10 total experts, 10 of 15,000 in the model. And that we found astonishing. Okay, so this is just a quick result. And however, today, this talk that we would like to give you guys here is not about the results and the shiny, bright moments. This talk was in this morning by Henrik and Robert. We would like to give you an insight in the work we do at TNG AI Research, what we are doing and how we do this. So we would like to deep dive. And so some of you might think, hey, that sounds fun. I would also like to have a brain scan of my large language model. What do I need? How could I do that? So we will tell you. But to be honest, in January this year, we did not start at zero. Instead, at TNG, we for a long time now have our own GPU cluster, where we run our own hardware and deploy open weight models on our own. We do this for several reasons. First, because this way we can provide to our clients fully data protected and sovereign AI, meaning we can guarantee that the tokens literally do not leave our hardware at any moment. That's important. Second, of course, we as TNG like to stay ahead of things. We like to observe the market. And usually when a new model is dropped, let's say Monday morning, we have deployed it Monday before lunchtime. We have benchmarked it over the night. And then on Tuesday morning, we can already drop it again because it was just a hype. But this is how we work. This is what we like to do. And third, of course, this enables us, this hardware and also the architecture around it, to perform these experiments. And we gave it a name. We call it our Skynet. So you might ask, what is Skynet? That looks fancy. And I have bad and good news for you. The bad news is that there is a talk about Skynet at Big Tech Day, but bad news is this is just right now in the Kohle bunker. Good news, though, is two good news. First of all, you can watch this later on YouTube, and I would recommend to do so. And also, I'll try to give you a short summary of Skynet. What is Skynet? Skynet are two things. First of all, it's the hardware. So we are GPU poor, but we have some hardware. And here you see a really happy managing partner of TNG, Robert Dahlke, founder of the AI research team, who with his own bare hands puts in a H100 graphics card into one of our nodes. Nowadays, we have several nodes. We moved him to a trusted data center nearby Munich with only us having access. And so we have not a lot compared to US competitors, let's say, but we have a bunch of 24 H100s, some H200s, some more exotic AMD AMI 325X GPUs. So in total, over 5 terabytes of free RAM. So something that we can have fun with and something that we can serve our own consultants more than 100 million tokens every day. So that is nice. And we, of course, combine them with our engineering capabilities. So on top of this, there runs a distributed Kubernetes stack where we deploy several AI APIs, several inference engines behind these APIs. And of course, because we have a really productive setting that is nowadays also used by our clients, we also have everything around that. We have authorization, monitoring, auxiliary stuff like database management, and a whole team, partly full-time, partly in the free time, working on that. And that is Skynet, and this is what we could use when we started in January, so this is why we were able to be so quick on getting these results. So, but now you say, okay, I need the GPU cluster in my basement. Okay, let's say I have this. Let's say you have your GPU cluster in your basement or in a trusted cloud. What do you do next if you want to have these nice brain scan pictures, let's say? Okay, let's do together a little crash course, how to deploy your own large language model. If you deploy a large language model, it's not super difficult. It follows usually this kind of process. You start over there with Hugging Face. Hugging Face is the kind of GitHub for open weight models. So every model that is open weightly published, you can find usually on Hugging Face. So you go there and you download your favorite model. What you get from that are two kind of things. First, you get the weights of the models. Here, this omega ij. Which are just very, very big matrices with tons of floating point numbers, really huge. And you get a little bit of configuration, some JSON files maybe, which tell you how exactly those should be put together. And then you take these two things and you feed them to your inference engine, nicely hosted in Skynet, of course. Today we use VLLM. Other favorite examples are SGLang, for example. And this engine and does the sophisticated work. It takes the weights together with the configuration and essentially implements this abstract architecture that David just showed you in a way that it works. So the tokens are processed and provides an API to the user that can use it then actually directly via API or via any chat tool that you like. So that is just the basic process how to deploy a large language model. Now we had a task, right? We want now to create these brain scan pictures, right? We're still adding, okay, how to get these pictures. The point of attack is right here. So when we ask ourselves, okay, now we want to look into the network, what it's doing, we have to look where it is doing that, and this is right in the inference engine. So let's look into that. So as I said before, the inference engine essentially implements the different layers of your model, what the architecture that David just showed you. So more or less, it is not rocket science to find for every kind of layer you see here, in the end, a Python class that implements this exact layer. And if we are now interested in this particular question, where for this brain scan, so meaning which experts are active, how active are they, we have to look where are these experts calculated. And this happens in the gate. The gate before this feed-forward networks of the experts, this is the point in the inference where the model decides which experts are selected and how much. So this is where we have to look at the implementation of that. And then you just do some full text search in the end or something more clever, and you find a function that is called select experts. And it returns you a tuple of weights and top KIDs, and it's bingo, this is exactly the information that we need. At this point, you extract this in some way, and you can produce the nice images that we saw. And as well, what you can do when then you have identified this Mr. Doom here, you want to switch off or on experts, you again can adhere plug in your own logic. That's what we did. So just write some TNG code and say, nice gate that you found these experts for me. How about I have a better choice? And you turn on and off experts as you like. So this is what we did. Briefly meaning we took the typical life cycle of a large language model and just slightly patched VLM in this case, meaning we got a nicely adapted API and could directly via requests to the inference network tell which experts in this time should be either prohibited, so deactivated, or enforced. And this is how we got to, first of all, these nice brain scan images, and then also to the results of steering the alignment of a large language model as DeepSeek. So that was part one. And we're now talking about like January, April in this area. That was the first experiment, and we thought, wow, that's nice. This is really nice new tool we have here. We can play around with that. We can get results. What to do next? What else could we do to utilize now this MOE architecture that we now better understood? What could we do? And let's think big, right? Our partners, managing partners, like to think big, and Robert immediately say, yeah, we have to think bigger. What if we not only inside one particular model turn on and off experts? Wouldn't it be nice to be outside the box? Wouldn't it be nice to say, okay, I have remember, I have this whole family of DeepSeek models. There's V3, there's R1, there's R1, 05, 28, and so on. A whole bunch of different models, and they all come with their own experts in some sense. Couldn't I just deploy one model and take an expert from another model and put it in the first model? And couldn't I play with that and see what happens? Yes, of course we could, and that's exactly what happened in the next step. This is when we start with our merging models approach. So how do we do that? Again, we are today about the deep dive in the nerd talk. Okay, so let's rephrase the idea. The idea is we want to have like one model, take an expert from another model, put it in the first model, roughly speaking. Let's keep this as an idea. Where should we go? Where should we go? Exactly this time, the point of attack is here, in the weights, when we've downloaded them from Hugging Face. Why in the weights? Let's again look one step further in the VLM implementation in the inference. How does, again, the inference work? What is an expert? Well, I said, again, we have here this abstract diagram of our DeepSeek architecture. And here, these blue things are the feed-forward networks that are exactly these experts. Let's look into them, but this time a little more abstract. What is an expert? Well, it's a feed-forward network. I'm a mathematician originally. For me, this is more or less a function consisting of a nonlinear part, an activation function, and then some linear part inside. Even if you have no interest in that, if you have never heard that, not important. What important is that only a small part of that actually is decided by the download of the model. Most of it is decided by the architecture, meaning only this matrix A and the B is the thing that you get via the weights. Everything else is the architecture, which is the same for all the DeepSeek models. So, meaning, if you want to exchange the experts in the same architecture, you have to exchange this A and the B, which are one-to-one, exactly those weights that you download from Hugging Face. So what you can do, it's quite simple. You download those weights from Hugging Face, but this time not only for one model, for a favorite one, but for the whole family, for V3, 03, 25, for R1, for R1, 05, 28. You download all these different weights, and then you put them together as you like. What does this mean? So once more back to our workflow here. So instead of just downloading one model and deploying it to your inference engine, let's do a little detour. Instead, we download many models, and then we combine them as we like. We choose factors lambda, parameters lambda, where we say that fraction of this model, that fraction of this model, and combine them and get new models. Quite a simple idea, rather astonishing. It actually works. And you can do this quite fully. You can merge only the experts. You can merge only one layer. You can merge different types of layers, whatever. Important thing here is this happens fully offline. So we often asked, how do we train that? No, we do not do any fine-tuning here. We do not do any post-training. This is really just simple a model merging, and this is all done offline. It's done on disk. It's done by a CPU even. You could use GPUs for sometimes, but it is on the CPU. Usually takes a few minutes, depending on your hardware, can be longer, can be faster. You also then adapt slightly your configuration file. You get a new model, a merged model, feed it into an inference engine, and that's it. And that's essentially what we did with R1T. That was the point there. And well, once R1T was out, of course, you know Henrik and Robert by now, we wanted to go further, we wanted to do more. And there's one bottleneck here is actually for us, because we are lazy people. This is rather expensive in the sense that you do it all the time offline. This takes not a long time, but if you do many, many models, it gets time-wise expensive. And each time you produce a 700 gigabyte model that you store on disk, and you have to tidy them up. And we thought, okay, because we're now in a moment in, like, say, April, now May or June, where we start to produce really lots of models, not one a day, like many a day, many a week. Nowadays, we deploy sometimes over 100 models a day, actually. So can we improve on this from an engineering point of view? Yes, of course we can. Let's rephrase it a little bit in the sense that we say, instead of doing this work on our own, let's the inference engine do this work. So what we now do is actually, we download all the models, but the weights we make available to our engine, and we just define a generalized format of our configuration of the model, and then on startup, without having to save them on disk before, our patched VLM version live merges our models for us. And this was like one of the key performance improvements, how we're able to really systematically search for more and more models. And at least for some special case, we even got one step further. At some point we thought, yeah, but still we have to redeploy the model every time, which takes some minutes. And if you want to have really a quick search, maybe minutes are even too much. Can we be even faster? And at least in some special cases, we can be. Because what you also could do is when we have, let's say, a rather big node, which fits like 2 full models onto, and luckily we have these AMD machines, which fit 2 full DeepSeek copies in the VRAM at once. So you could just, like, on start, load both model weights of 2 models into the VRAM, and then live, on request, you can let the user provide, actually, via API call, an adapted JSON, and then the model live merges from the loaded models in the VRAM, your new merged model. And this is then how you can really quickly test out and systematically search through your merged model space, at least in some special cases. Yeah, so that is the technique behind model merging. So all the colleagues asked me, how do you do it? This is how. And then why? Well, this is one of the diagrams from our paper to show you why do we do that. So what you see here is that every of these blue squares are like one model and one batch of models they produced. So it's one model merge. And the 2 axes are the following. On the y-axis, we have the relative inference cost, meaning how verbose is the model, how many tokens does it produce in a typical prompt that we tested here. And then from the left to the right, we have the factor lambda, which in this case is exactly the R1 ratio. So here we mix V3 or 325 with R1, and the ratio lambda is how much of R1 is in that model. Meaning on the left, 0, we have the full V3 model, and on the right, we have 100% R1 in some sense that David will explain you in more detail. And well, not surprising, what you see here, interestingly, is the more R1 is in the model, the more verbose it gets, which is not surprising because R1 is a reasoning model, a reasoner, while V3 isn't. And an interesting artifact here is that we have these 2 branches here, which was a very important discovery for us, and David will turn on this in a second, but just in a second, because I would like to wrap up now my part here. So what we are trying to do here today is to give you an insight. What is AI research doing? A lot of colleagues ask me all the time. And I think you got now a feeling for what we're doing and how we do it. And I would like to summarize as follows. So the first big part in our daily work is really MLOps. So this is not to be underestimated. It's really time-wise maybe the biggest part. It's deploying these models, keeping your pipeline running, dealing with different GPU architectures, dealing with upgrades of VLM, and so on and so on. So this is a lot of engineering. Then, of course, with the type of research that we are doing, it's all about models, models, models. So we produce tons of models, like not only the 80, like let's say official or semi-official ones Henrik mentioned, like really hundreds of models in the end that we test out in this or another sense. And if you have tons of models, you need to evaluate them. So it's all about evaluation, running benchmarks in several senses. Of course, also doing vibe checks, so other kind of checks. And in our daily work, when we sit together in Zoom, it's really often like a lot of hours staring at plots. So we stare at a lot of different plots, starting with the boring one from Grafana, just to see that they're actually up and running our models, up to way more interesting plots where we look into the hidden states and compare the hidden states of different models to each other. There was an interesting LinkedIn post recently by TNG, or X-Post. Or we compare the different models to each other. We look at differences in the tensors exactly and try to figure out whether we can learn something from that. And naturally, of course, all the time we look at benchmark plots, like testing our models, how well do they perform as we expect them to do, and so on. That is our daily work, which we are doing now for 8 months, roughly, right? And yeah, luckily we had some successes. And for this, I hand over to David again.
So after this little cliffhanger by Fabian, let's return actually to this plot here. And now Fabian has hidden some details actually about the different models here, because now you see there are two different markers for the models here. The squares denote full merging models. So this means that really all components, all parts, self-attention layers, router, experts, routed experts, shared experts, and so on, are combined in a model merge. So for these models, it makes totally sense that they approach here, they converge here again. If you increase this R1 fraction, they converge to the behavior of R1, because up there, it's simply R1 again. And for these circles here, only the routed experts are merged, or the weights of these routed experts are combined. So you might have already wondered about actually this model here. This means then that here, in this case, for this model here, the routed experts, the weights of the routed experts come from R1, and all the other parts, shared experts, router, self-attention, comes from V3 O3 24. And as you see, they have really interesting properties. For example, this model here only has 60% of the relative inference costs compared to R1. So we thought, maybe these models have interesting properties as well, other interesting properties as well. And then we looked at this plot here, which again shows here the inference cost, but this time on the horizontal axis. And on the vertical axis, this time an intelligence score, in this case measured by two benchmarks. One is called AIM24, quite popular, and another one, MT Bench. In the meantime, since we produced this plot from our paper, we did a lot of other benchmarks, but I think this serves the main point. We looked again for the model, and we saw, oh, our model is here, actually, which you've seen before on the previous slide, on the previous plot. And this means that although the inference costs are only at approximately 60%, it's almost as intelligent as its parent R1. This is interesting, right? And we thought, well, let's publish this. This is actually, out of this whole bunch of models, this is the first Chimera. So to sum this up, if you compare to its parents, it got smarter than V3 O3 24 and faster than R1. But shortly after that, only approximately 1 month, DeepSeek didn't stop there at these two models, and they published R1 0528, so the update of the reasoning model R1. But we didn't stop there either, actually. And we again tried via the same construction mechanism as Fabian explained. We tried, in this case, to combine 3 models, V3 O3 24, R1 and its update. and via a little bit more sophisticated approach, which also involves, for example, the attention layers, we arrived actually at the R1T2 Chimera, which in some sense, if you compare it to R1, is both faster and smarter than R1. So we were able, in this space of or optimization space of inference costs and an intelligence score, to push this Pareto frontier quite a bit. Therefore, we decided that we should publish this. This might get some interest. And if you're not a TNG employee, you can, for example, either if you have enough GPU power, you can download the weights from Hugging Face you can find here, or you could use the model via OpenRouter, which also was mentioned by Henrik and Robert. And if you're interested in more details, we also published the construction method on arXiv, so check out our paper. Okay, well, there was one little problem after the update, and Fabian will tell you.
Thanks. So, we come to the end. But of course, we have one more thing, as it's common. Because this is Big Tech Day, and we are TNG consultants, and we would hate to let you go home without having learned something today. So that's now the educational part here. Of course, there were obstacles. Like it sounds so simple, and maybe it's not rocket science, but there were definitely obstacles. And like maybe one insider story today in the talk by Henrik and Robert, Henrik said sometimes you have to say if it's shit, then it's shit. And if you have seen this talk, you might have wondered what was one of these that shit moments. One downside of R1T2 was that it couldn't do tool calling at the beginning. Even when it published it, it couldn't do tool calling, and we found that was rather shit, to quote Henrik here. But we resolved it, and let's see how we did that. Two things that we should clarify before that. First of all, what is tool calling? And second, how does it work in general? So what is tool calling? Tool calling means that when you send a prompt to your LLM, you can give it some more functionality. For example, you're running an agent, and the agent interacts with your large language model, and it can tell the LLM, hey, you know what, I have a weather tool here. You can call it if you need the weather information. And then if in some of its answers, the model has the feeling that it would need to know the current weather information, then it can respond to the agent, oh, you know what, please call this weather app for me so I know the weather information. And then the agent will respond with this result to the large language model. So that is what tool calling is, and it's a rather important technique in this whole agentic frameworks that we're using today. And how this works technically is depicted here. And I think the most important thing to remember really at this point, which sometimes is forgotten, is that a large language model is always only tokens in, tokens out. Let's put this simplified for today. It's, let's say, text in, text out. What I mean by this is a large language model itself does no tool calling. It has no functionality to really go to a website and download something, to look for the weather. It has no functionality to run Python code. No, a large language model is a generative AI that takes token in and puts tokens out. So what does this mean in this tool calling context? When you send a tool call, or your agent does, to your large language model, it calls usually an API. And it provides a structured format, usually JSON. And in this JSON, it says, you know what, LLM, there's a tool, there's here the my tool. You could use it if you want to. And this is a structured format JSON. Now, the first task that your inference engine has to do, it has to translate this JSON in something the LLM understands, and that is just text. So meaning it takes your JSON, what you send it, and then it takes a so-called chat template, which it uses to render your structured information into the prompt, which is then actually fed into the large language model. And so when you give it a tool, the prompt that's actually put into the model could then look something like this. And it says in the system, by the way, when a tool call is needed, you must use the following format, use the issue. So please, when you, LLM, want to use the tool, then start with tool call begin, and then give me the information what kind of tool call you would like to make here. And so the LLM takes this and responds. And if the LLM then really wants to do this tool call, it responds this way and says, yeah, you know what? I would like to call my tool now. And it does so by putting out the tokens tool calls begin, tool call begin, and so on and so on. And then again, this is not what you as a user or the agent would like to have. Then again, it's a duty of the inference engine to take this output and translate it into a structured JSON format so that the answer that you as a client receive contains then a section tool calls, which tells you, I should call this tool for my model. So this is the tool calling workflow. And this is just a general thing for any large language model, how this works. So, but it didn't work for R1T1. That was our R1T2. That was our problem. Why? Well, it's all about the genes nowadays. The issue is that R1T2 has 3 ancestors, and bummer, only 2 of those 3 support tool calling. R1 is a model which did not support tool calling. And we thought, that's bad. What can we do about that? However, the thing is, when you understand this workflow of tool calling from a technical point of view, this does not hinder you to just use it. Right? So this is pure prompt engineering in some sense. You take your message with your tools, you have your chat template, and you translate this into the prompt, you feed into the network, and you could expect this, well, I told you if you want a tool call, then just do it. So why shouldn't R1 just do this? But turned out R1 did just not call tools. Or let's say also R1T2, our model, did just not call tools. And we wondered why. And at some point, we figured out the issue lies in here. Because when you have a close look at this prompt, you discover that these 2 guys here, which are like framing the structured output for R1 tool calling, those are actually special tokens within the R1 tokenizer or the V3 tokenizer. And apparently, R1 is just not trained to understand these tokens. These are just gibberish for it. And in particular, it would never output them because it doesn't know what to do with it, so it just forgets about it. It's like random noise. So clearly, this did not work. What works, though, is we looked around, and there are other great models on the market who also support tool calling, for example, the QN family, and they have similar instructions. They also just prompt the LM, you know what, give me this kind of output format for a tool call. But the difference is that QN does not use special tokens. It's just using some XML-like structure, like this tool call tag here, which is just usual text, no special tokens, which is understood by actually any model. And it turned out this worked well. And this worked very well also for R1T2. And this is how we were able to resolve the issue for R1T2. But even more interesting, it even resolved the issue for R10528, because we observed that in typical tool calling benchmark, with this kind of chat template, with this instruction, even R10528 was better in tool calling than with the original DeepSeek method, which we found interesting. And this is just one of the many obstacles that we had to resolve. And this is how, in particular, we resolved tool calling.
Exactly. But, well, this is the end of our journey. Yeah. True. From mixture of tunable experts, when you think back to the brain scans and deactivating single experts, and model merging with the chimeras in particular, up to tool calling. But this is only the end for now. There's more to come, so stay tuned. Here are our LinkedIn contacts, and your questions are welcome. Thank you for your attention.
Thanks.
Yes, thank you both for the talks. I think we have 5 to 10 minutes for questions, and I already saw a hand here, so I'll just pass over.
Yeah, thanks for the great talk. Did you also experiment with different sizes? I'm not sure if every DeepSeek model comes in different sizes, like 8 billion, 200 billion or so. First part of the question, and then second part, quantization. Did you look at quantization in order to save memory and speed up things?
Yes. So about sizes, there is right now in our big Techday showcases the artist that was mentioned this morning as well exhibited, and this is actually a super large language model which is double the size of DeepSeek, this we can tell. So yes, the first question, but nothing that we published in that sense. And about the second question, actually not. We thought about it, whether quantization is a thing, because there are also different quantizations of the DeepSeek models available. But no, we have not invested in this some time, to be honest.
But at least we've seen that, for example, when we did the current research, we've seen that already at our basic quantization, which is by standard used by DeepSeek, which is a floating point format called BF16, I think. There are actually some numerical instabilities occurring due to this quantization already. So this really has an effect, yeah.
Okay, I'll take one more question from the first row, and then I'll come through the back.
Thank you for the talk. So at the beginning, you looked at these brain scans and then identified specific, what are they called, routers, experts. But then later when you combine things, you just went by the numbers, right? You didn't really try to learn anything about the brain of the model anymore?
You mean regarding when we move to model merging?
Yeah, when you said like, we're going to take X% from that model.
That is,
this is
part of ongoing research, I would call it this way.
Yes, now combining.
Yes, we think about it.
Okay. Yeah,
different ideas.
Maybe it's
a lot.
something. I don't know.
Yeah.
Hopefully, maybe not.
Thanks for the very great talk. I have a question. The slide where this little circle was right in the middle, for me it looked like there were more circles that were higher in intelligence and lower in cost. Why didn't you pick those?
Yeah, I exactly knew that when we give this talk in this TNG audience, this question will come. The reason is this is just really, that's a real plot. In this way, in the real plot, I mean that we run really quick checks. We deploy very, very many models, and what we sometimes do not do is extensive benchmarking. And benchmarking is an art on its own. You have various instabilities or statistical effects. You have, first of all, if you do longer prompts, you have sampling, right? And then also, actually, we have some numerical issues sometimes which do influence the result. So what we saw here was only 2 benchmarks. That's one thing, and actually old ones like AIM24 and MT Bench, as well as to be honest, in this particular plot, the numbers are not very great, the sample rate. So it can be that once jumps over our sample for R1. In general, we test them all, of course, better before releasing them, and also had the internal, TNG wipe checks and all that stuff. But yeah, so it can happen that one point jumped a little bit ahead, but this is not then the reason to just jump at the model right away. Of course, we considered it, but overall, the R1T model was in this case really the most promising one.
Yeah, and as Henrik and Robert mentioned this morning, actually, they both looked always at somehow the vibe or the persona of the models they got. Yeah. So they felt that this is a nice model to chat with and so on, and so this also went into the decision to pick this one.
I know this question will come with TNT. That's great, yeah.
Okay, I saw one more hand here, and then I'll return over there for the last question. And then if anybody else has more questions, I'll put you on the spot and promise that you'll stay for a couple more minutes afterwards.
Thank you guys for the talk. I was wondering, when you merge like one reasoning model and one non-reasoning model, I mean, one is trained to start with this thinking block and one is not. How does this interplay? Does it think sometimes or half a time or?
That is like, of course, it depends on what exactly you merge, but I can shortcut this question because there's one diagram in this paper which exactly shows that we have also the ratio of R1 on the x-axis, and interestingly, in this particular subset of models, there's a breaking point, a transition point at around 50%, not exactly, but around 50%, where it jumps up, where suddenly the reasoning starts. Like meaning in the end, the think token plops up in the probabilities at this point and gets number 1, and this is, but there's a turning point indeed.
For me, as a trained theoretical physicist, it looks really like a phase transition somehow of when it starts to think.
Okay, then I'll take the last question over here.
Thank you. My question is, when you reassemble a new model with different kind of experts, did you also have to change the router to actually know how to call these different experts? And my second question is, did you also did you only use the benchmarks to identify whether the model is now better or more capable, or did you also be able to extract what the expert is actually doing?
Yeah, this is also ongoing research. Both questions, actually, answers to both questions. Yeah. So we are also investigating the router, and this is a complicated issue because if one, for example, somehow wants to modify or customize the behavior, then one also needs to adjust router because if the input is not routed to the experts you modify, then nothing happens, right? Yeah. Do you want to add something, Fabian?
No, I don't want to add something, but it's a very good question.
Yeah. Yeah.
Okay, with that, I'll thank you all for your attention, and the next round of talk starts at 2:55, so you have around 14 minutes left to change rooms. And thanks a lot, and on behalf of the partners, I also have a gift for you. Thanks for putting in the work, for coming here and preparing this talk. It was very insightful, and I wish you all a pleasant rest of the afternoon. Thank you.
Thanks for joining.